Good morning, respected judges. We are Team Saras Crew, and our project focuses on generative AI based cloud removal and reconstruction for LISS 4 satellite imagery. Cloud cover is one of the biggest challenges in optical remote sensing because it hides valuable surface information. Traditional cloud masking simply removes cloudy regions, resulting in incomplete datasets. Our motivation was to reconstruct those missing regions using complementary SAR information, enabling reliable imagery for various applications. Rather than designing a new model immediately, we followed a structured three-stage research methodology. We first benchmarked state-of-the-art diffusion models, then analyzed why they could not be directly transferred to LISS-4 imagery, and finally designed a new framework specifically to address those real-world challenges. As the first phase for our study, we benchmarked two leading diffusion models, confidence-guided latent diffusion and conditional Brownian bridge diffusion. Both models were trained and evaluated using Sentinel-1 SAR and Sentinel-2 optical imagery using identical pre-processing and evaluation settings, ensuring a fair comparison. This benchmark allowed us to understand the strengths of current diffusion-based approaches before moving to a LISS-4 specific solution. Both benchmark models produce high-quality reconstructions and establish a strong performance baseline. However, while they performed well on well-aligned Sentinel datasets, these results also highlighted an important limitation. Their success depended heavily on paired SAR optical data, which is not readily available for LISS-4 imagery. This observation led us to the key research question: why do these models perform well on Sentinel data but struggle with LISS-4? We identified three major challenges: differences in geometry, differences in spatial resolution, and the absence of accurately paired SAR LISS training data. Instead of forcing impossible pixel-level correspondence, we decided to redesign the pipeline around geometry-aware alignment and multi-modal learning. Our proposed framework transforms the problem into a geometry-guided reconstruction task. Instead of searching directly for corresponding Sentinel-1 patches, we first generate a geometry-consistent synthetic SAR representation using EO2 SAR diff. This synthetic SAR acts as a bridge between optical and radar modalities. We then perform structure-aware partial optimal transport to identify the most structurally similar real Sentinel-1 SAR patch within a larger search region. Finally, the cloudy LISS-4 image, the synthetic SAR, and the aligned real SAR are jointly pre-processed using a three-branch ESR format, enabling accurate cloud reconstruction even without pixel-perfect correspondence. Our final reconstruction network is a three-branch ESR format that jointly processes the cloudy LISS-4 image, synthetic SAR, and aligned real SAR. Each input is encoded independently, allowing the network to preserve modality-specific information before fusing them through multi-scale transformer attention. A global attention bottleneck captures rich contextual features, and the decoder reconstructs a cloudy-free LISS-4 image with skip connections and restormer refinement, producing high-quality analysis-ready output. The framework is built entirely using publicly available datasets, open-source geospatial tools, and modern deep learning frameworks. We combine LISS-4, Sentinel-1, and Sentinel-2 imagery with EO2 SAR diff, ESR former, and diffusion-based models supported by GDAL, ECSNAP, Rasterio, and PyTorch. The modular design makes the framework scalable, reproducible, and suitable for operational deployment. Beyond cloud removal, our goal is to create reliable analysis-ready imagery for real-world Earth observation. The framework can support agriculture, food monitoring, disaster management, urban planning, and environmental monitoring. Because it relies on publicly available satellite data and open source technology, it remains cost-effective, scalable, and ready for future integration with additional ISRO sensors and advanced generative models. To make our benchmark evaluation more interactive, we also developed this web-based demonstration platform. Here we can select either the confidence-guided latent diffusion model or the conditional BBDM model. Choose the evaluation dataset such as the Sentinel or the SpaceNet 6 and run inference on any SAR image. The platform performs real-time SAR to optical translation and then compares the generated optical image with the corresponding ground truth, making it easy to visually evaluate the reconstruction quality of both benchmark models.